Derivative of a quotient is our theme today. So if we have just one term, right, we take the derivative. Piece of cake. Okay? We've talked already if we have a product. So if we have two pieces multiplied together where we can take the derivative of each of them, we have to do the product rule. Today we're learning the quotient rule. So this is when you have one function or item, whatever, divided by another function. And they are both something that you can take the derivative of, so we're not just talking like a whole number or something. Then we're going to talk about the quotient rule. Now, this is your fancy smancy explanation.
It's going to do better when we actually do it.
Exactly. It's going to do better once you actually apply it. But basically, so f being the top function, g being the bottom function. So f being your numerator, g being your denominator. Now, beware. When we do product, it's derivative of one, keep the other. Plus, and then flip-flop that scenario, right? And we can flip-flop that scenario and not worry about which do we, just do the opposite. It's a plus, it doesn't matter. This matters now. You have to be more focused on keeping the same process. So, derivative of the numerator times the denominator, as is. Then it's subtracting, and now you flip-flop, derivative of the denominator times the numerator as is. And then it's all over the original denominator squared. Okay? Learn it, know it. Okay, derivative of the top times the bottom minus derivative of the bottom times the top. All of the denominator squared. Okay? If I was a singer, if I could remember, I mentioned Verge and Mark in AP Classroom. Verge will sing, and I'm trying to remember, I need to sit down and think about what it is. Something about high D low minus low D high or something. Like the derivative of the top, so high D low, so derivative of the high being top, low being bottom. Derivative of the top times the low, so high D low minus low D high. Derivative of the low times the high. So high D low minus low D high over low squared. I can't remember how she does it, but something along those lines. Figure out what works for you. We're ready? Example 1. F of x is natural log of x over 2x plus 3. Find f prime of x. Okay. So we're going to start by taking the derivative of the top. So derivative of natural log of x is 1 over x times 2x plus 3, the denominator as is. Then, important, minus, okay, product rule is plus, quotient rule is minus. That should kind of make sense in some form of your brain because that equivalence is often there. Now it's derivative of the bottom. So derivative of 2x plus 3, 2, times the numerator of natural log of x. All over 2x plus 3, quantity squared. Okay. First of all, good news that 2x plus 3 quantity squared, we'll probably just leave it as 2x plus 3 quantity squared. That's not something you necessarily multiply out normally. On occasion you might have to, but more often than not I feel like it gets left as is. The numerator. Okay. You will find with quotient rule there are a vast number of ways they leave their answers. There's not one right simplified answer that is like the primary answer. Now, what I will say is this is probably not a good form to leave because
you could do 2x plus 3 over x, right?
You can, but then you still have a fraction within fractions. And that's the not fun part there. Does that make sense? And so, in order to get rid of a fraction within a fraction, really what we need to do is get rid of this denominator of x. How do I get rid of a denominator of x? You multiply by x, right? And so what I'm going to suggest here is that we multiply the numerator by x. If you multiply the numerator by x, you have to multiply the denominator by x. And the idea now, again, we're multiplying by x over x, and x over x is equivalent to 1, so it's okay to multiply by x over x. We're not changing any value, we're making it equivalent. So now when we multiply x, well, first of all, we have 1 over x times 2x plus 3. The x and 1 over x will cancel, and you're just going to be left with 2x plus 3 minus 2 times ln x is 2 ln x, right? Times an x is going to be 2x ln x, and then just leave it as 2x plus 3 quantity squared in the denominator. I definitely will not say that that's the only way you could leave it.
So you have the x on the denominator, we have to put an x down there.
Oh, yeah. Yeah.
Me and Ethan both at the same thought. But
I'm like, okay, what are they questioning? Oh, they're probably questioning. I was thinking you guys were going to question something about the numerator. And then I'm like, wait, why are they questioning the denominator? What'd I do? Okay, sorry. Yeah, don't follow my example there. Make sure you actually multiply the denominator by x. Okay? And what I will say, because here's what I thought you guys were going to question this front part of 2x plus 3. But what I will say, you know, these are multiplied. So when you're multiplying that x, it's multiplying by that whole thing, right? It's not an x times this and an x times this. Okay? If you distributed this beforehand, or like Ross, you mentioned 2x plus 3 over x. So 2x plus 3 over x times x over 1. The x's would cancel. Or that's his thought was that. My thought was, okay, if I make this 2 over x plus 3 over x. No. X's would cancel. 2 plus 3 over x. If I distributed the 1 over x and then multiplied the x, we still end up back at 2x plus 3. Okay, so there's different ways you could get this to work. Leaving the x out of the denominator, that was a no-go, though. That was just a mistake. Okay. Other questions on this one? Yes?
So, could you not cancel the 2x plus 3 on top?
You cannot, because this 2x plus 3 on top is not a factor. If this was 2x plus 3 times 2x natural log of x, we could, because they'd both be factors. But this 2x plus 3 has something else added or subtracted to it, so we cannot. Okay. And we will see some canceling. I don't necessarily know if it's in this part of today's lesson or not, but we will possibly see. We will see some as we go through stuff. So, okay, we good? Okay, example 2. Find d of x. I don't know if you guys remember from the beginning of the year, but that is not a common way, but that is a way to represent derivative. So this is saying find the derivative with respect to x of x cubed minus 2x plus 2 over sine x. So, see if we can do a little better this time. See if I can do a little better. Okay, so where are we starting?
so you take the derivative of f. Multiply it by 2x.
Okay, so derivative of f. What's f? The top. So derivative of x cubed minus 2x plus 2. 3x squared minus 2 times sine x. Notice, I just put that 3x squared minus 2 in parentheses. Those parentheses would be necessary, because that's a quantity, then times sine x. And now I'm going to subtract.
Derivative of the bottom must be cosine x
Derivative of sine x is cosine x
times x to the third minus 2x plus 2.
times x to the third minus 2x plus 2, because that's the numerator.
Sine squared.
Notice I put that x cubed minus 2x plus 2 in parentheses, right? All over.
Would it be sine squared x or sine x squared? Like sine x inverted?
So I would probably write it as sine squared x. The other, so for note, sine squared x is equivalent to sine of x in parentheses squared. If you say sine of x squared,
It's taking the sine of x squared.
that's not the same. Okay? So these two are equivalent. This has a different value. Get the picture? And I don't care which way you write it. Both notations are good. So I think sine squared x is more the maybe simplified version. Okay. Okay. In my notes, I have written there are ways to simplify if we want to. But then I have this answer boxed.
We don't have to
We
want
don't
to.
want to.
Okay. In other words, are there possibly things we could do? Yes. I mean, we could take that sine x and distribute it by the first two terms. We could take that cosine x and distribute it to 3 terms. But we're not going to get any like terms that you could add or subtract. So I have this as my boxed answer. No one said these answers looked neat today, right? You will learn that very quickly. Quotient rule can get ugly very quickly. Okay. And I'm going to write a comment. There are ways to simplify. And I will use the phrase if necessary. And of course, obviously, AP multiple choice, you need to be able to recognize, if you do a derivative and you get this answer and it doesn't match any of the answers, start seeing, okay, what kind of things are equivalent. Okay, ready for the next one? Okay, example 3. Let y equals cosine x over e to the x plus x. Find dy dx. Okay, there you go. Dy dx equals. Your help from me. Where'd you start?
Take the derivative of the top.
Derivative of the top. So derivative of cosine x is negative sine x times the denominator. So e to the x plus x. Notice I'm using parentheses anytime my numerator denominator is multiple terms. Then what?
We do minus the derivative of the bottom,
Minus derivative of the bottom.
which is e to the x plus 1
Derivative of e to the x is e to the x. Derivative of x is 1
times cosine x
times the numerator as is, cosine x.
over e to the x plus x quantity squared.
E to the x plus x quantity squared. That is one where I definitely would not multiply that denominator out unless I had a definite reason. I mean, it's just, multiplying e to the x times e to the x, it's not something we normally do. So I would leave it as that denominator is that. Now, in relation to Jacob's question earlier, now the question becomes, can I cancel this e to the x plus x with this e to the x plus x?
I don't think so, because you're subtracting from it, right?
Right. So if our last term also had an e to the x plus x, we could. But it's an e to the x plus 1, so we cannot. Now, we will talk about what what the book tends to do is they will sometimes break it into 2 fractions. And if you break it into, negative sine x e to the x plus x over e to the x plus x squared, well, in that fraction, an e to the x plus x can cancel. Minus, the second fraction would just have to stay as is. E to the x plus 1 over cosine x times cosine x over ex plus x quantity squared. I thought, I have the answer key as this. or my notes as this. But if you had to divide into two fractions, which we'll talk about at some point, you might see that. Okay? And I guess something, if you do want to, you could flip around and put cosine x in front of e to the x plus 1. It's not necessary, though. Okay. Find the differential dy of y equals x over cosine x.
So that's the same thing as finding the derivative, right? Because it would be dy would be the only y on the left side, so you get dy is equal to the derivative on the other side, right?
Yes, but when you're doing the derivative of all the x terms, you also have to put in your dx. Okay, so when we use differentials, each time you take a derivative, you are tacking on the differential with respect to whatever variable that is. Okay? So the idea here, I mean, they're kind of talking like if it was implicit, but it's not. So it's not extra hard, really. But so the derivative of y, officially it's 1, right? But then it's a y value. So then we say 1 dy, or in other words, just dy. On the right, we have a fraction. So it's derivative of the numerator. Derivative of x is
1 dx.
1 dx, and then it's times cosine x. I'm going to come back and clean this up later, because this isn't going to be in a good form that I would leave my answer as. And then we're going to subtract. And now it's the derivative of cosine x, which is negative sine x. That's an x term, so we're going to say dx. And it's still times x all over cosine squared x. Okay. Cleanups I would do, there's a couple different ways. We could do this. First of all, if I say 1 times dx times cosine x, I don't have to write the 1, and I could say cosine x dx. Minus a negative is going to make this plus. We have an x, we have a sine x, and we have a dx. So I would say x sine x dx. All over cosine squared x. There is one other variation. Pull out the dx, and I would normally put it at the end because it's the differentials, and that's where we think about differentials going. And that's the answer I have circled in my notes. Oh my gosh. Try that again. Okay, dy. So I have, when we pull out that dx, I'm left with cosine x plus x sine x. And then if I put parentheses around all that and a dx at the end, over cosine squared x. So I can make the comment. The shortcut in this case would have been, if we would have started with the derivative of y being dy dx, done the derivative of the x's all normal, then we could have had, if it's dy divided by dx, we could have multiplied the dx off to the right. That is equivalent and acceptable. Does that make sense what I'm saying? It's like instead of putting dx's here, if we would have had dy over dx,
You can just take the derivative and multiply dx.
you can, yeah, dy dx, it's weird, but it works like a fraction. You can separate those pieces, and if it's divided by dx, then you can multiply dx over to the other side. So I've taught you guys to use differentials. If you see if it's derivative of a y term, use dy. If it's derivative of an x term, use dx. You will often see, and I debate which is easier. I like the way I teach it to begin with. You will often see sometimes where when they use differentials, if they're trying to find dy dx in the end, every place they take derivative of a y term, they'll put a dy dx. And then when they take derivative of an x term, they don't have to put anything after it. And I don't know. I like it, I don't like it. So, but you will see that sometimes. Okay.